Docker Overview. Docker is an open platform for developing, shipping, and running applications. Docker enables you to separate your applications from your infrastructure so you can deliver software quickly. With Docker, you can manage your infrastructure in the same ways you manage your applications. By taking advantage of Docker's methodologies for shipping, testing, and deploying code quickly, you can significantly reduce the delay between writing code and running it in production. The Docker Platform. Docker provides the ability to package and run an application in a loosely isolated environment called a container. The isolation and security allow you to run many containers simultaneously on a given host. Containers are lightweight and contain everything needed to run the application, so you do not need to rely on what is currently installed on the host. You can easily share containers while you work, and be sure that everyone you share with gets the same container that works in the same way. Docker provides tooling and a platform to manage the life cycle of your containers. Develop your application and its supporting components using containers. The container becomes the unit for distributing and testing your application. When you're ready, deploy your application into your production environment, as a container or an orchestrated service. This works the same whether your production environment is a local data center, a cloud provider, or a hybrid of the two. What can I use Docker for? Fast, consistent delivery of your applications. Docker streamlines the development lifecycle by allowing developers to work in standardized environments using local containers which provide your applications and services. Containers are great for continuous integration and continuous delivery workflows. Consider the following example scenario. Your developers write code locally and share their work with their colleagues using Docker containers. They use Docker to push their applications into a test environment and execute automated and manual tests. When developers find bugs, they can fix them in the development environment and redeploy them to the test environment for testing and validation. When testing is complete, getting the fix to the customer is as simple as pushing the updated image to the production environment. Responsive deployment and scaling. Docker's container-based platform allows for highly portable workloads. Docker containers can run on a developer's local laptop, on physical or virtual machines in a data center, on cloud providers, or in a mixture of environments. Docker's portability and lightweight nature also make it easy to dynamically manage workloads, scaling up or tearing down applications and services as business needs dictate, in near real time. Running more workloads on the same hardware. Docker is lightweight and fast. It provides a viable, cost-effective alternative to hypervisor-based virtual machines, so you can use more of your compute capacity to achieve your business goals. Docker is perfect for high-density environments and for small and medium deployments where you need to do more with fewer resources. Docker architecture. Docker uses a client-server architecture. The Docker client talks to the Docker daemon, which does the heavy lifting of building, running, and distributing your Docker containers. The Docker client and daemon can run on the same system, or you can connect a Docker client to a remote Docker daemon. The Docker client and daemon communicate using a REST API, over Unix sockets or a network interface. Another Docker client is Docker Compose, that lets you work with applications consisting of a set of containers. The Docker daemon. The Docker daemon listens for Docker API requests and manages Docker objects such as images, containers, networks, and volumes. A daemon can also communicate with other daemons to manage Docker services. The Docker client. The Docker client is the primary way that many Docker users interact with Docker. When you use commands such as docker run, the client sends these commands to Docker, which carries them out. The Docker command uses the Docker API. The Docker client can communicate with more than one daemon. Docker Registries. A Docker registry stores Docker images. Docker Hub is a public registry that anyone can use, and Docker is configured to look for images on Docker Hub by default. You can even run your own private registry. When you use the Docker pull or Docker run commands, the required images are pulled from your configured registry. When you use the Docker push command, your image is pushed to your configured registry. Docker objects. When you use Docker, you are creating and using images, containers, networks, volumes, plugins, and other objects. This section is a brief overview of some of those objects. Images. An image is a read-only template with instructions for creating a Docker container. Often, an image is based on another image, with some additional customization. For example, you may build an image which is based on the Ubuntu image, but installs the Apache web server and your application, as well as the configuration details needed to make your application run. You might create your own images, or you might only use those created by others and published in a registry. To build your own image, you create a Docker file with a simple syntax for defining the steps needed to create the image and run it. Each instruction in a Docker file creates a layer in the image. When you change the Docker file and rebuild the image, only those layers which have changed are rebuilt. This is part of what makes images so lightweight, small, and fast, when compared to other virtualization technologies. Containers. A container is a runnable instance of an image. You can create, start, stop, move, or delete a container using the Docker API or CLI. You can connect a container to one or more networks, attach storage to it, or even create a new image based on its current state. By default, a container is relatively well isolated from other containers and its host machine. You can control how isolated a container's network, storage, or other underlying subsystems are from other containers or from the host machine. A container is defined by its image as well as any configuration options you provide to it when you create or start it. When a container is removed, any changes to its state that are not stored in persistent storage disappear. Example Docker run command. The following command runs an Ubuntu container, attaches interactively to your local command line session, and runs bin bash. Docker run Ubuntu bin bash. When you run this command, the following happens. 1. If you do not have the Ubuntu image locally, Docker pulls it from your configured registry, as though you had run docker pull Ubuntu manually. 2. Docker creates a new container, as though you had run a Docker container create command manually. 3. Docker allocates a read-write file system to the container, as its final layer. This allows a running container to create or modify files and directories in its local file system. 4. Docker creates a network interface to connect the container to the default network, since you did not specify any networking options. This includes assigning an IP address to the container. By default, Containers can connect to external networks using the host machine's network connection. 5. Docker starts the container and executes bin bash. Because the container is running interactively and attached to your terminal, you can provide input using your keyboard while the output is logged to your terminal. 6. When you type exit to terminate the bin bash command, the container stops but is not removed. You can start it again or remove it. The underlying technology. Docker is written in the Go programming language and takes advantage of several features of the Linux kernel to deliver its functionality. Docker uses a technology called namespaces to provide the isolated workspace called the container. When you run a container, Docker creates a set of namespaces for that container. These namespaces provide a layer of isolation. Each aspect of a container runs in a separate namespace, and its access is limited to that namespace. The Docker dashboard. Before going too far, we want to highlight the Docker dashboard, which gives you a quick view of the containers running on your machine. The Docker dashboard is available for Mac and Windows. It gives you quick access to container logs, lets you get a shell inside the container, and lets you easily manage container lifecycle. What is a container? Now that you've run a container, what is a container? Simply put, a container is simply another process on your machine that has been isolated from all other processes on the host machine. That isolation leverages kernel namespaces and groups, features that have been in Linux for a long time. Docker has worked to make these capabilities approachable and easy to use. What is a container image? When running a container, it uses an isolated file system. This custom file system is provided by a container image. Since the image contains the container's file system, it must contain everything needed to run an application, all dependencies, configuration, scripts, binaries, etc. The image also contains other configuration for the container, such as environment variables, a default command to run, and other metadata. We'll dive deeper into images later on, covering topics such as layering, best practices, and more. Info. If you're familiar with Groot, think of a container as an extended version of Groot. The file system is simply coming from the image. But, a container adds additional isolation not available when simply using Groot. Share the application. Now that we've built an image, let's share it. To share Docker images, you have to use a Docker registry. The default registry is Docker Hub and is where all of the images we've used have come from. Docker ID. A Docker ID allows you to access Docker Hub, which is the world's largest library and community for container images. Create a Docker ID for free if you don't have one. Create a repo. To push an image, we first need to create a repository on Docker Hub. 1. Sign up and share images using Docker Hub. 2. Sign into Docker Hub. 3. Click the Create Repository button. 4. For the repo name, use Getting Started. Make sure the visibility is public. Private repositories. Did you know that Docker offers private repositories which allows you to restrict content to specific users or teams? Check out the details on the Docker pricing page. 5. Click the Create button. If you look on the right side of the page, you'll see a section named Docker Commands. This gives an example command that you will need to run to push to this repo. Push the image. 1. In the command line, try running the push command you see on Docker Hub. Note that your command will be using your namespace, not Docker. $docker push Docker getting started. The push refers to an image does not exist locally with the tag Docker getting started. Why did it fail? The push command was looking for an image named Docker getting started, but didn't find one. If you run docker image ls, you won't see one either. To fix this, we need to tag our existing image we've built to give it another name. 2. Log in to the Docker Hub using the command docker login or username. 3. Use the docker tag command to give the getting started image a new name. Be sure to swap out your username with your Docker ID. Docker tag getting started your username getting started. Now try your push command again. If you're copying the value from Docker Hub, you can drop the tagname portion, as we didn't add a tag to the image name. If you don't specify a tag, Docker will use a tag called latest. 4. Docker push your username getting started. Run the image on a new instance. Now that our image has been built and pushed into a registry, let's try running our app on a brand new instance that has never seen this container image. To do this, we will use Play with Docker. 1. Open your browser to play with Docker. 2. Click Login and then select Docker from the drop-down list. 3. Connect with your Docker Hub account. 4. Once you're logged in, click on the Add New Instance option on the left sidebar. If you don't see it, make your browser a little wider. After a few seconds, a terminal window opens in your browser. In the terminal, start your freshly pushed app. 5. Docker run dp 3000 your username getting started. You should see the image get pulled down and eventually start up. 6. Click on the 3000 badge when it comes up and you should see the app with your modifications. Hooray! If the 3000 badge doesn't show up, you can click on the Open Port button and type in 3000. Recap. In this section, we learned how to share our images by pushing them to a registry. We then went to a brand new instance and were able to run the freshly pushed image. This is quite common in CI pipelines, where the pipeline will create the image and push it to a registry, and then the production environment can use the latest version of the image. Now that we have that figured out, let's circle back around to what we noticed at the end of the last section. As a reminder, we noticed that when we restarted the app, we lost all of our to-do list items. That's obviously not a great user experience, so let's learn how we can persist the data across restarts. Persist the DB. In case you didn't notice, our to-do list is being wiped clean every single time we launch the container. Why is this? Let's dive into how the container is working. The container's file system. When a container runs, it uses the various layers from an image for its file system. Each container also gets its own scratch space to create update-remove files. Any changes won't be seen in another container, even if they are using the same image. See this in practice. To see this in action, we're going to start two containers and create a file in each. What you'll see is that the files created in one container aren't available in another. 1. Start a new Ubuntu container that will create a file named data.txt with a random number between 1 and 10,000. Docker run ubuntu bash c shuf-i1-10000-n1 no data.txt and entail fdev null. In case you're curious about the command, we're starting a bash shell and invoking two commands. The first portion picks a single random number and writes it to data.txt. The second command is simply watching a file to keep the container running. Validate that we can see the output by Xing into the container. To do so, open the dashboard and click the first action of the container that is running the Ubuntu image. You will see a terminal that is running a shell in the Ubuntu container. Run the following command to see the content of the data.txt file. Close this terminal afterwards again. Cat data.txt. If you prefer the command line, you can use the docker exec command to do the same. You need to get the container's ID and get the content with the following command. Docker exec cat data.txt. You should see a random number. Now, let's start another Ubuntu container and we'll see we don't have the same file. 3. Docker run ubuntu ls. And look. There's no data.txt file there. That's because it was written to the scratch space for only the first container. 4. Go ahead and remove the first container using the docker rmf command. Container volumes. With the previous experiment, we saw that each container starts from the image definition each time it starts. While containers can create, update, and delete files, those changes are lost when the container is removed and all changes are isolated to that container. With volumes, we can change all of this. Volumes provide the ability to connect specific file system paths of the container back to the host machine. If a directory in the container is mounted, changes in that directory are also seen on the host machine. If we mount that same directory across container restarts, we see the same files. There are two main types of volumes. We will eventually use both, but we will start with named volumes. Persist the to-do data. By default, the to-do app stores its data in a SQLite database of etc. to-do.db in the container's file system. If you're not familiar with SQLite, no worries. It's simply a relational database in which all of the data is stored in a single file. While this isn't the best for large-scale applications, it works for small demos. We'll talk about switching this to a different database engine later. With the database being a single file, if we can persist that file on the host and make it available to the next container, it should be able to pick up where the last one left off. By creating a volume and attaching it to the directory the data is stored in, we can persist the data. As our container writes to the to-do.db file, it will be persisted to the host in the volume. As mentioned, we are going to use a named volume. Think of a named volume as simply a bucket of data. Docker maintains the physical location on the disk, and you only need to remember the name of the volume. Every time you use the volume, Docker will make sure the correct data is provided. 1. Create a volume by using the docker volume create command. Docker volume create to-do-db. Stop and remove the to-do app container once again in the dashboard, as it is still running without using the persistent volume. Start the to-do app container, but add the flag to specify a volume mount. We will use the named volume and mount it to etc. to-dos, which will capture all files created at the path. Docker run dp 3000 to-do-db, etc. to-dos getting started. Once the container starts up, open the app and add a few items to your to-do list. 5. Stop and remove the container for the to-do app. Use the dashboard or Docker PS to get the ID and then Docker rm to remove it. 6. Start a new container using the same command from above. 7. Open the app. You should see your items still in your list. 8. Go ahead and remove the container when you're done checking out your list. Hooray! You've now learned how to persist data. Note: well-named volumes and bind mounts are the two main types of volumes supported by a default Docker engine installation. There are many volume driver plugins available to support NFS, SFTP, NetApp, and more. This will be especially important once you start running containers on multiple hosts in a clustered environment with Swarm, Kubernetes, etc. Dive into the volume. A lot of people frequently ask, where is Docker actually storing my data when I use a named volume? If you want to know, you can use the Docker volume inspect command. Docker volume inspect to db. The mount point is the actual location on the disk where the data is stored. Note that on most machines, you will need to have root access to access this directory from the host. But that's where it is. Accessing volume data directly on Docker Desktop. While running in Docker Desktop, the Docker commands are actually running inside a small VM on your machine. If you wanted to look at the actual contents of the mount point directory, you would need to first get inside of the VM. Recap. At this point, we have a functioning application that can survive restarts. We can show it off to our investors and hope they can catch our vision. However, we saw earlier that rebuilding images for every change takes quite a bit of time. There's got to be a better way to make changes, right? With bind mounts, there is a better